we discuss some two-dimensional problems. What does it mean? No, basically, your standard segment tree is one-dimensional data structure. So you have one-dimensional array. So you have like array A, and you make one-dimensional requests. So you calculate something on a segment. Segment is one-dimensional thing, right? So you have this one-dimensional segment, and you calculate something on that segment. But basically, life is not always one-dimensional. So sometimes you need to take care of some two-dimensional operations, or even three-dimensional operations, or even more. So sometimes you need to answer questions which are two-dimensional. And today we learn how to we learn two techniques. One technique is how to use one-dimensional data structure to answer two-dimensional queries, and another technique which will kind of make two-dimensional data structures in the same way we make one-dimensional data structures. So this like a special technique, not very special, but some kind of technique, which allows you to make two-dimensional data structures to answer the same two-dimensional queries. So let's go. So first let's start with the following problem. Let's have some simple two-dimensional problem. One of the simplest two-dimensional problem we will learn is the following. Let's say we have some rectangles. So simplest two-dimensional object is a rectangle. So let's have some rectangles. And let's put one more. And something here. Yeah. And one more here. So you have some rectangles on a plane, and you have some requests. So each request is a point. So you have some points in this plane. And you need to answer for each point. You want to calculate the number of rectangles which covers this point. It's too boring. Let's move it here. Yes, and let's move it here. So for each point, we want to find the number of rectangles which covers this point. So for this point is 0. For this point is 1. For this point is 1. Here is 2. For this point is 0 again. Here is 1, here is 1, 2, 3, and 0. Very basic problem. And now we'll solve this problem using a technique which is called a sweep line. So the sweep line technique works as follows. So we need to answer some queries in two-dimensional plane. So what we will do, we will reduce this problem to one-dimensional problem. It can be done in a very simple way. We'll create a line. Let's make a vertical line. And we will move this line across our picture. So we'll start from the line in the far left, and we will move this line to the right. And each time we will maintain the current state of this line. So we will maintain not the state of the plane, but only the state inside this sweep line. That's the plan. Basically, we will split the plane into some vertical lines, and for each vertical line, we will answer the query. That's the idea of this technique. So what happens when we move this line to the right? What we need to maintain. So when we move this line to some point, so when we have some point here, and when we move the line to this position, we will need to answer the query. So for this point, we need to find the number of segments which cover, or number of rectangles which covers this point. So inside this line, is basically a one-dimensional problem. So if you look inside this line, I'll just transfer this line here. So this is your sweep line. In this sweep line, you have these two rectangles, first rectangle, second rectangle. So if you make a projection of this rectangle to this line, you will have some segment. Yeah? So this rectangle is this segment, and this rectangle is this segment. And that's your point. So your point is somewhere here. So this is this line. Yeah? So now when you need to answer this query, you need to answer the following problem. You have some segments, and for given point, you need to answer how many segments cover this point. Right? This is a basic one-dimensional problem which can be solved using segment trees. That's the whole plan. So again, we will move this line from far left to the right, and each time we find some point which is inside our sweep line, we will answer the queries corresponding to this point. So for this point, we will be able to answer the query. And we will answer these queries using a segment tree, because in the segment tree, we know how to solve this problem. We know how to find the number of segments which cover this point. How to solve this problem using a segment tree? The easiest way is the following. Let's split all the y coordinates into some segments. So for each segment, the number of rectangles covered at this point is always the same. So we will take all y coordinates of all borders of all rectangles. I need some more colors. Let's take all y coordinates of all rectangles. Too many of them. Now this picture is kind of busy, but that's fine. So I just split all the y coordinates into some segments. We need to number rectangles segment tree. No. We'll need only one segment tree. Yeah. Well, just a minute. Again, I will split all the y coordinates into some segments. And for each segment, for each this small segment, I will maintain the current numbers, current number of the rectangles which covers this particular segment. So we start from far left. When this line is in far left position, all segments are covered by 0 rectangles. So we'll put number 0 in all elements of this structure. Now, when we move this line to the right, at some point these numbers will be changed. When we will change? We will change when we find some border of some rectangle. So when we move from this position to, let's say, this position, too many lines on this picture. So when we move to this position, we now, what is the difference between this position and this position? Difference is that now we have this rectangle, so these segments are now covered by one rectangle. So we have this, here we have 0, here we have 1, 1, 1, 1. Here we have again 0, 0, 0, 0, 0. So after we find this left border of this rectangle, we need to increase this number for all segments inside this rectangle. Right? Now again, we move this line to the right, then we find this left border of this rectangle. So when we find this left border, again, now these segments are covered by one more rectangle. So we need to increase this number for all segments inside this rectangle. So we find these 3 segments and increase this number by 1. So we have here, we have 2, 1 and 1. All other numbers are the same. Yeah, we actually don't care about how big coordinates are. In this technique, we actually may have any coordinates, even not integer coordinates. We just have all these y coordinates, put in here, sort them, and split all possible y coordinates into some segments. So here we'll have about n segments, so 2n segments. Yeah. So we have 2n different. If we have n rectangles, we have 2n different borders. So here we have up to 2n segments. Right. So we actually don't care about how big coordinates are. Even if coordinates are big, they still split this line into some 2n segments. That's all. Okay, that's basically also. So when we find the left border of some segment, we just increase all the numbers inside this rectangle by 1. So now we have this point. So when we have this point, we have this state of the data structure. In this data structure, we have something like, we have 0, then 1, 1, 1, 1, 1, 1. Here we have 2. Here we have 1, 1, 0, 0, 0. So this is just this state rotated 90 degrees, right? So we look on our point, see in which segment this point lies to. So here this point is inside this segment. So our point is inside this segment. This segment has number 1. It means that this point is covered by exactly one rectangle. That's all. That's the whole technique. And when we find the right border of some rectangle, we decrease the number by 1. So when we move from this position to this position, we see this right border of this rectangle. And we just decrease all these values by 1. That's good. That's all. So we need a data structure which can maintain 3 types of requests. So we need to have the following request. We need to have plus or minus 1 on segment. And find the current value of the element. Current element. And we just have even more complicated data structures before. So this is can be very simply implemented using segment trees, or even Fenwick trees. You can do it using Fenwick trees. It doesn't matter. So now we just use a segment tree to maintain the current state of our sweep line. So when we again, what happens? So when you have the left border of the rectangle, so you move from here to here. You take all segments inside this rectangle. So here you have some segments. You have plus 1 for all these elements. When you see the right border of the rectangle, again, you move from here to here. You need to take all segments here and make minus 1 for that segments. And when you have a point inside your sweep line, you just find the current value of the segment corresponding to this point. So you can find this segment using binary search. It's simple. So when you have the point, you need to find the segment corresponding to this point. You can do it using binary search. Now, again, you have all these y's in a big sorted array. So you just find your y coordinate in this sorted array, and you will find the index of this segment. Okay. It's quite simple, right? So that's all. And what will be the total time complexity? So first we need to sort all these y's, sort all these x's, and so Again, first you need to sort all the y coordinates to find this set of segments. Then you need to sort all possible x coordinates, because you want to apply these operations in the following order. So you want to apply operations from left to right. So you kind of put all the x coordinates in another big array and sort this array by x. Yeah. So now you can go from left to right and apply all these operations in correct order. That's all. So this all takes you n log n time, both these two sortings. And here you can make both these operations in log n time using segment tree. And you have at most 2n such events. So for each rectangle you have one event when you have the left border and another event when you have the right border. So you need to make up to n operations on a segment tree. Each operation costs you log n time. So total time complexity will be n log n. Cool. That's all. That's one of the simplest implementation of the sweep line method. So simplest application of sweep line method. I don't want to make an implementation yet. I believe you can do implementation yourself. So implementation is pretty simple. You just sort all these y's, get all these segments, make a standard segment tree, then get the list of all possible events, sort this list by x, and then apply these events one by one. When you see this event, you add one. When you see this event, you subtract one. And when you see this event, you find the value and put this value in the result. That's all. It's quite simple implementation. After you implemented the segment tree, it's actually very simple. Okay, that's all. Well, that's one of the easiest problems solved by sweep line method. Sweep line method is actually very powerful. You can make a lot of various operations using the sweep line. How to see if your problem can be solved using sweep line? Basically, what you need to solve is to check if your problem can be solved in one vertical. So if you can solve the same problem in one dimension, so if you have this one line, you need to think how to solve this problem when I have this vertical line. If you can solve this problem inside your vertical line, then you think, is it possible to change the current state of data structure when I move from one vertical line to another vertical line? You need to see what changes need to be made to your data structure and to see if these changes can be made using your segment tree. If you can make this change using the segment tree and you can make this operation inside one vertical line, then you can perform a sweep line method. So you just iterate from left to right, apply the operations, and that's all. That's how your sweep line method works. Good. Let's solve one more problem because it's kind of tricky. I will leave some more problems in the home task. Again, we have home task, and we will discuss it tomorrow. Last time we had only one submission. It was kind of sad. So I expect to have more submissions because when I don't have anything to discuss, it's kind of boring to have discussion of home task when I have no home task. Let's discuss one more problem. It's like kind of classical problem about sweep line and this technique. The problem is the following. Again, you have some rectangles and you want to calculate the total area of the union of all these rectangles. Area of union of rectangles. No, it's kind of boring to have area of intersection of all rectangles. So when you want to calculate area of intersection of rectangles, it's kind of boring because the intersection of rectangles is always rectangle. Yeah? If you have two rectangles, the intersection is always a rectangle, or it's empty. So area of intersection is kind of boring. So, but area of union it's much more interesting. So in this picture, for example, I will ruin this picture. I want to calculate the area of this figure. So I need to have this plus this, and also this, and also this, and this, and that. Yeah. So I have this figure. Is it clear? I don't think it's clear. Well, it's fine. So I have this strange picture with hole in the center, and I want to calculate the total area of this figure. Let's go. So how to implement this? Again, first, let's solve this picture. Let's solve this problem in one-dimensional case. So if you have one-dimensional case, so you have only one line, and each one-dimensional rectangle is a segment. Yeah. So you have some segments on this line, and you want to find the total length of all points covered by at least one segment. So you want to calculate total length of this union. Assign find sum. Makes sense. Yes, you can do it using a segment tree with two operations. So first operation is to assign value. So we will assign one to. So if you have zeros here and ones here, then what you need to do? Oh, actually, you don't need ones. That doesn't matter. So you need to assign one. Let's think that all segments have equal length. So if all these segments have equal, so you split your line into segments of equal length. So each small segment have length equal to 1. So you need two operations: assign one to the segment and calculate the sum on a segment. Yeah. And you can do these two operations using segment tree, right? We discussed this. So assignment and sum are good operations. They are associative, they are distributive. What else? Well, that's all. So you can make a segment tree with these two operations with lazy propagation, like we discussed. Perfectly normal. It will work. No problem. No, actually, if you have different lengths, let's see. In this problem, we actually have different lengths of these segments. So in this problem, each segment has some length. So we don't need this sum. We need to something different. We need to sum of all lengths. What's the length? Such that they have equal to 1. So we need something like this actually. But it's just a small tweak to your segment tree. You can make this function in your segment tree with no big difference. Just when you apply operation assign one to the segment, then this sum will be equal to sum of lengths of all segments in your subtree. Yeah, makes sense. So you just maintain the sum of all segments in your subtree. It's simple. And when you make assignment operation to your segment, you make this sum equal to the total length of your segment. Yeah, that's a good question. What happens when you remove a rectangle? This solution is good in one-dimensional case, but it's kind of tricky to transfer it to your two-dimensional picture, because when you move from one line to another, these ones and zeros will be changed in some strange way, right? So when it's easy to add more rectangles. So if you find the left border of some segment, you just assign one to this segment, right? You just take you kind of add another segment to this picture. So you add another segment. You need to assign one to all elements of this segment, and so on. But when you find the right border of the segment, you need to remove the segment. And when you remove the segment, some elements should become 1 and some element should become 0. So like here, if you remove this rectangle, you need to make zeros in this position, but not in this position. And it actually may be complicated. So if you have a lot of small segments and one big segment, so now you have all elements equal to 1. So we have here all elements are 1s. But when you find the right border of this rectangle, so you need to remove this big segment, you need to put zeros in these positions. And we don't know how to do it fast, because it's strange operation. It's not segment operation. We need to put zeros in some random positions in our array. It's not a segment operation. So we need to find another one-dimensional solution. So this one-dimensional solution is good in one-dimensional, but it can be transferred to your problem, because you cannot move from one solution to another solution. So we need to find different solution. Let's move back. What we can do? We can increase by 1 and decrease by 1. Let's use this solution and try to adopt it to our problem. So we will, instead of having these 1s and 0s, we will have various integers, and this integer will be the number of segments covering this point. So here we have 2. Now it is simple. Yeah. So for this picture, we can change this picture when we move from one line to another line. Again, we use like the same procedure. When we have left border, we increase the segment by 1. When we have the right border, we decrease segment by 1. But now we need to find a way to calculate the total length of all non-zero elements. So we need to find when all elements are non-zero, so greater than 0. That's what we need to find. So we need to have a segment tree with 2 operations. First operation is plus minus 1 on segments. And another operation is to find the total length of all non-zero elements. That's all. That's the problem we need to solve. And this problem actually can be solved using segment tree. Any ideas? What's the problem here? Problem here is that again, some elements may become 0 or non-zero in random. So again, if you have the same picture, yeah. So if you have the same picture, you have a lot of 1s, but when you remove this, you have some zeros inside the segments, and the position of the zeros is kind of random. So we kind of need to be able to perform this operation on some random elements. But we can do it. The idea about how we can do it is very simple. Let's change this problem. So this sum is actually, so if you want to calculate this sum, it is the same, is the sum of all elements minus the sum of 0 elements. So minus sum of len I for this I equal to 0. So this sum is constant. Yeah. So all we need is to find a way to calculate this sum. So we need to find a way to calculate the total length of all 0 elements in our array. And we actually did about the same data structure in some home task discussion. Again, let's have all elements have length equal. So if all length equal to 1, so all we need here is to find number of zeros. Number of elements equal to 0. Can you do this segment tree? So I need segment tree with 2 operations. First operation is to increase or decrease the segment by 1, and second operation is to find the number of elements equal to 0. Just let you some time to think. So if you watch my Code Forces lesson about segment trees, I discussed almost the same problem. And if you was on the last Contas discussion, we discussed almost this problem in last Saturday. Oh no, not last. It was on the first. Yes, I believe it was on the first Contas discussion. Okay, give you some more hints. So, hint is very simple. All elements of this array are non-negative. So all elements in this array are always non-negative. Yeah, good thinking. So if we want to calculate number of zeros after we make -1, then on the previous step, when we make before we make -1, so if we have -1, and after this -1 operation, we need to find number of zeros, right? It means that before this operation, we need to know the number of ones. Yeah? So we have some array. 3, so if you apply -1 operation to this array, you will have this array. And in this array, after you apply this operation, you want to know the number of zeros. You want the number of these zeros. It means that in this segment, you want to know the number of ones. So I want to know the number of ones. That's a good start. Yeah. That's actually a very nice idea. So in this array, I want to know the number of zeros. In this array, I want to know the number of ones. Now let's think about what number we need. We actually need to know only one number in this for each segment. And again, if you apply -1 to even more, so let's have one more operation. So if you have one more -1 operation, so here we have 3, 2, 4, 2, 4. So to be able to know this number of ones, so in this array, you want to know the number of twos. Yeah, so these twos. So you want to have, for this array, you want to know twos. Yeah, that is very simple. All we need to know is the number of elements equal to minimum on this segment. So we will maintain, we discussed this in previous lecture, we'll maintain the pair of values. We'll maintain minimum on the segment and the count of minimums. So it's number of elements equal to minimum. And we can recalculate this value when we apply this operation. When we make plus or -1 to the whole segment, we will just increase or decrease this minimum. This count will be the same. And we can recalculate this pair from the pairs of our children. Because this is actually a combination of these two segments is some associative function. So if you know for one segment, for another, if you know minimum here, count here, then using these two numbers and these two numbers, you can recalculate the minimum on a whole segment and the number of minimums in this whole segment. That's all. And you can just use the same approach to calculate the sum of lengths in the same way. So instead of this counter, we will calculate not the number of minimums, but the total length of elements equal to minimum. Yeah. So you calculate the minimum on the segment and the total length of all segments which have this minimum. And that's all. And you can recalculate this number when you make a combination of two segments. And you can recalculate them when you apply this operation. So when you apply this operation, again, this minimum is changed by this counter is not changed. And when you combine two segments into one, you just take the minimum of these two minimums. If minimum is different, you take one counter. If minimum is the same, you take the sum of these counters. Good. That's all. And now we take this data structure and apply it to our two-dimensional case. So we just, again, we move from left to right. Each time we maintain this picture, so we maintain the number of rectangles covering all segments of our segment tree. And when we have left border, we increase by 1. When we have right border, we decrease by 1. And each time when we move our sweep line from here to here, so when we move sweep line from one position to another position, so between two events, you just increase your final result by the length of this. So this is delta x, and it should be multiplied by the total length of all segments covered by at least one rectangle. So you take this formula, so you take the total length of all segments minus length of all segments not covered, get the total length of all segments covered by at least one rectangle, multiplied by delta x, and add it to result. That's all. That's all. Okay, this one is not very trivial tasks about sweep line. Most of problems about sweep line are pretty trivial. So you just go from left to right and see what operations you need actually for your segment tree. Usually it's kind of, so usually if the problem is solvable by sweep line, it's kind of obvious. So you see what operations do you need. You see if it is possible to build a segment tree with operations you need. Sometimes, usually it's kind of trivial that you kind of find what operations you need, see these operations are associative, so you can make a segment tree, that's all. Sometimes it's kind of tricky, like here. Last part again, which part is last? Again, we have the following segment tree. We have a segment tree with two operations, plus minus 1 on the segment, and find the total length of all segments with value at least 1. So, like this. Now we use this data structure to calculate the total area. How we calculate total area? We go from left to right, and each time we move our sweep line between two events, so we have event here and some event here. Between two events, the state of this data structure is the same. So when between two changes of the state of the structure, we have a segment when we have the same picture here. So we just take the length of this segment multiplied by total length of all segments covered by at least one rectangle. So again, you take this segment between two events. So we have like event here. Let's ruin this picture once again. So we have event here and another event here. So inside this strip we have these rectangles should be added to our result. So this area is the width of this area multiplied by the height of this area. The width is just the difference of axes of these two events, and with height is just the sum of all segments which covered by at least one of rectangles. So you calculate this sum multiplied by delta x and have the total area of this union of rectangles, and then you add it to the result, and that's all. Approximate algorithm maybe in the end of the course we'll talk some. It's maybe only some basics. We'll see. Okay, that was the first part. So this is the first technique which is widely used when you need to solve some problems about some two-dimensional problems using segment trees. Let's solve one more before I erase this picture. Let's solve one more problem. So let's say if you have some picture of rectangles, you have some number of rectangles, and again you have some points. For each point you need to answer how many segments cover this point, but you don't have all these points in advance. So you're given these points one by one, and you need to answer the question for each point in online. So you're given some point, you need to say for this point how many rectangles covers this point. So the same problem like the first one, but we don't have this point or all points in advance, so we need to answer all these requests one by one. So what can you do? You can do the following. You can make the same sweep line technique. So you can perform this sweep line technique, but do it in a persistent way. So you, instead of having just simple segment tree, you make a persistent segment tree. And now when you have a persistent segment tree, you kind of remember all the states of this segment tree. So when someone asks you, so again, you just run your sweep line from left to right and remember all the states of this sweep line. And now when someone gives you some point, so someone gives you this point and asks you what is the number of rectangles covers this point, you look in your persistent data structure and find the state of the sweep line corresponding to this x coordinate. So for these x coordinates, you have some state of the sweep line. So you find this state of the sweep line in your persistent data structure. And for this state of the sweep line, you answer this query. So if you want to answer some queries in online, you just make a sweep line before, like in pre-calculation, you make this sweep line, remember all the state of the sweep line in persistent segment tree, and then when you need to answer the query, you find the corresponding state of your sweep line and get the result from this state of the sweep line. That's basically when you may want to use some persistent data structures. So mostly persistent data structure used in some two-dimensional problems. So you have two-dimensional problem, you use one of the dimension as like time of your persistent data structure. So all different lines correspond to different states of your data structure. And when you need to answer query, you find the state of your data structure corresponding to this vertical line, and then find this result of in this state of your data structure. Whew. Okay, now so that's all about sweep line I want to talk about. So we will have some more sweep line problems in the home task, but I think we get all the basics. Now I want to move to next problems because we have all time. Next topic. Let's try to build two-dimensional segment tree basically. So I try to show you a technique which will allow you to modify your data structure to make it two-dimensional. So basically, not only two-dimensional, you can add any dimensions to your data structure. So again, what is the segment tree? Segment tree is data structure, which, like very basic data structure, very basic segment tree, which allows you to make two requests. So you have some segment. I just love to write small segments here. So you have some array, and you have two requests. First request is to set a value of some. Let's make it increment like in Fenwick tree just for simplicity. So we'll increment value in ij by b. I plus equal b. So I just added second dimension. So basic, it's basic segment tree. And you have some sum on the segment, which returns the sum from I from left to r minus 1. So that's the basic one-dimensional segment tree. Now we'll try to make the same in two dimensions. In two dimensions, you have two-dimensional array. So you have this. You have this table. So this is 1D. This is 2D. In 2 dimensions, we have this 2-dimensional array, like table, and we have, again, we have the same requests. First request is to change the value in some cell of this table, so we'll increment I, j, v, which will increment the value of some element of this table. And the second operation is to find sum in some 2-dimensional segment. Two-dimensional segment is a rectangle, right? So we will have operation sum on some rectangle of this 2-dimensional array. So we have, let's have left, right, top, bottom. You will return the sum of sums for all I from left to r minus 1 for all j's from top to bottom minus 1 a I j. Just simple transformation, right? So here we have 1-dimensional requests. Here we have the same 2-dimensional requests. So we change the value of some element of 2-dimensional array. So we can take any element and make plus v to this element, or we may take some rectangle, yeah, and find the sum on this rectangle. So this is left, this is right, this is top, this is bottom. I have it in wrong order, right? Usually the first index is the row of the table. Just like this, you know? And here it's from left to right. Not a big deal, but just to make it clear. Good. Now, how to implement 2-dimensional segment trees? Very simple data structure. Let's have some 2-dimensional array. So let's have like 2-dimensional array 4 by 4. So this is your 2-dimensional array. There are some numbers here like 5, 4, 6, 1, 3, 7, 8, 6, 3, 2, 7, 1, 7, 5, 3, 6. Is it random enough? Yeah, good enough. So this is your 2-dimensional array. Let's make the following. First, let's make a segment tree over one of the direction of this array. Let's make let's take the first indices of this array and make a segment tree over this first dimension of this array. So we'll have something like this. So we'll have this 4 element. So this is a segment tree over the rows of this 2-dimensional array. So we have 4 rows of this 2-dimensional array. Let's have a segment tree of size 4. So for these 4 elements, each element corresponds to one row of this 2-dimensional array. Let's enumerate them. So like before, let's have this index 0. Let's have this 1, 2, 3, 4, 5, and 6. So this is your first segment tree. Now let's see. Each element of the segment tree corresponds to some segment of your array. Now, for example, if you take this, this node of your segment tree corresponds to this segment of your array. So this node corresponds to these 2 rows of your array. Basically, this element corresponds to this strip of your array. So it corresponds to these 2 bottom rows of your array. Now, what we'll do? We will put into this node another segment tree which will take care of the second dimension of your array. So in this node 2, so this node 2 will contain inside of this node another segment tree by another coordinates, by y coordinates. So you take the second dimension of your two-dimensional array and make another segment tree. So here we have let's have like this. So inside this node of your first segment tree actually is this segment tree. And inside each node of this segment tree is some segment tree by this second coordinate. Good. Again, you're too quiet. It's not how it's working. So just, if everything is clear, just say everything is clear every 30 seconds. Good. Now, in this, again, each element of this second segment tree, let's enumerate. Each element of this second segment tree corresponds to some segment by the second coordinate of your array. So if you take, let's use some more colors. Let's use red color. So if we take some element, let's say this one element. So this node of this segment tree corresponds to this segment of your array. And if you look inside, so this segment tree is inside this node. So this node corresponds only to this strip. And this node corresponds to this segment of this strip. So this node corresponds to this rectangle. That's all. So in this node, we will put the sum on this rectangle because this node corresponds to this rectangle of the array. So here we have value equal to 5, 10, 17. So in this node, we will have value 17. This 17 is the sum of all elements inside this rectangle. This rectangle, because this node corresponds to this segment, and this node is inside this segment tree. This segment tree corresponds to this segment. So this node corresponds to this segment of this segment. So it corresponds to this rectangle. Good. That's all. Let's fill all elements here. So here we have 3 plus 7 is 10. Here we have 7. Here we have 10 again. Here we have 7. Okay. My random generator is not very random. Okay. 17 here and 34 here. Let's change something just to make it more random. Let's make it 5. Just to make it look more random. That's all. That's all. So we make a first segment tree. In each node of the segment tree, we put another segment tree. And now we have this segment tree inside the segment tree, and each node of this inner segment tree corresponds to some rectangle of this array, and it contains the sum of all elements inside this rectangle. That's all. How to implement this? It's actually quite easy to implement. Basically, what we need is some, look here, what is the easiest way to implement segment tree is to implement it inside the array. So you make indices for all elements and make the array and just put these nodes in the array of like 7 elements. Yeah? So each element have some index, just put this element in using these indices. And now inside of each of these arrays, you need to put this segment tree. This segment tree also can be implemented using array. So you have array of 7 elements inside this array of 7 elements. So actually you need to maintain one array 7 by 7. So actually 2-dimensional segment tree is basically 2-dimensional array. So here you have array of arrays. It's a 2-dimensional array. So you make this array 7 by 7 and put these numbers inside this big 7 by 7 array. That's all. That's how you implement. And now how to implement operations. Quite simple. So let's have some operation. Let's have some operation. Let's have first operation. So what happens when you want to increment some number? No. No, let's say like you take some number here and you want to make +1 to this element. What you need to do, you need to find all the elements which contain this element of your array. Yeah, we put segment tree inside the segment tree, yes. West Coast Customs approved, no. So what happens when you increase one element of the array? You need to find all the rectangles which contain this element. How to find all the rectangles? Very simple. So you take the first segment tree, this first segment tree, and find all the segments which contains this element. So we need, if this rectangle is contain this element, it should contain it by this first dimension of your array. So how to do it? Very simple. You just make this same operation as you make in the regular segment tree. So you start from the root and find all these nodes on the path from the root to this element. So we take all these roots or all these nodes on this path, and each of these nodes contains some strip which contains our element. So this node contains this strip, this node contains this strip, and this node contains this strip. So we need these three nodes to be updated. In each of these three nodes, we need to update rectangles containing these elements. So how to find all elements containing this element? Well, we go into this subtree and find all the elements containing this element. Again, we do the same procedure. We just take all the nodes on the path from the root to this element. Not this. Stop. So first we make the standard procedure for the segment tree to find all nodes containing this element in this outer segment tree, like here. And then in each of these nodes, we call the same recursive procedure to find all nodes in this inner segment tree. Good. And in each of these segment tree, we just increase the value by 1, because this element will be increased by 1. Total sum of each segment will be increased by 1. So we have +1 here, +1 here, +1 here. That's the whole plan. Cool. So what will be the total time complexity? Total time complexity will be the following. So we need to find these nodes. Here we will have up to log n nodes. Yeah? And in each of these nodes, we will need to run this operation. And in each of these operations, we need to update these log n nodes. So we have log n small trees. In each of these log n trees, we need to update log n nodes. So it will goes to log n multiplied by log n. So the total time complexity of this operation will be log squared. Cool. That's all. Now, what about the second operation? How to perform the second operation? Again, we need to calculate the sum on sum. Oh, this picture is going to be. Oh, let me just remove something from this picture. Look. Now, what happened when we need to calculate sum on some rectangle? So in this second operation, you are given some rectangle. No, let's say something like this rectangle. So you have this rectangle, and you need to find the sum of all elements inside this rectangle. So how to do this using this structure? Again, you make the same procedure like in the regular segment tree. When you calculate sum on a segment, you make this recursive call and find all the segments which combines into your given segment. So you start recursion here, go here, take this segment, go back, then go here, take this segment. So this node corresponds to this segment, this node corresponds to this segment. Together, you have your segment by first coordinate. And then inside each of these nodes, you call the same procedure for this inner segment tree. So inside this inner segment tree, you go to, you take this node and this node. Cool. So first you make a recursive procedure in this outer segment tree, find these two nodes. In each of these two nodes correspond to some strip of your two-dimensional array. Inside of this node, you call same procedure by y coordinates. So you find these two segments. That's all. So you have these two nodes. In each of these two nodes, you find these two segments. So they will correspond to this rectangle, and this rectangle. Now you have some of this rectangle will just combine into your given rectangle. That's all. So again, this recursive procedure works in log n time, like before, and this works also in log n time. So total time complexity will be again log square. Cool. That's all. That's how you make two-dimensional data structures, basically. And you can add more dimensions to your data structure using this. So this is a common technique to add more layers of your data structure. Just some layering technique. So you have first layer of data structure in each node. You have the second layer. If you, for example, if you need three-dimensional arrays, then you can add another segment tree on top of this, like segment tree by z coordinate, and in each node of this segment tree by z coordinate, you have all this two-dimensional data structure. And again, to apply these two operations, you need to make a request in this outer third segment tree, and inside each of the node, you make this two-dimensional request. So total time complexity will be log cube. Cool. Can you make this in implementation? I think you can do kind of. I don't know how. I don't know the best way to implement this. I think you make some code for the segment tree and then put segment tree inside of the segment tree. I'm not sure how to do it using C++ templates. I believe you can do it using C++ templates. I'm not such a good professional about C++, but I believe you can make it just so the same code rather inside the same code. I'm pretty sure I can implement it in any object-oriented programming language. So you just make this class segment tree, and as an element you put another class of segment tree. I believe it's possible in mostly all programming languages, but if you're talking about efficiency here, I'm not sure about it. I think it will be kind of efficient. So if you just make a segment tree and using arrays, and then make a segment tree and put as an element another array, just make array of arrays. It should work just fine. I believe you can do it. So you can do it as an exercise. Just take your favorite programming language and try to implement this in the simplest possible way. Do we have more time? Yeah, we have time. So let's go talk about other data structures. Let's try to apply the same technique to all other data structures we discussed on previous lectures. So let's try to apply it to Fenwick trees and to sparse tables. Now, it is quite easy. We just do all the same thing, but in Fenwick trees and in sparse tables. For example, if you have two-dimensional Fenwick trees, how the usual Fenwick tree works. So in just regular Fenwick tree, you have this array f and f of I equals to the sum of all A j from from P of I to I. Like we discussed last week. Yeah. What happens in, so it's one dimensional then. It's one dimensional thing. 1D. So in two dimensional case, we will do the same but twice. So we'll have two dimensional Fenwick trees. So we'll have Fij. And each element of this two-dimensional array will maintain, like, again, we need to make Fenwick tree of Fenwick trees. Yeah? So this first dimensional is just Fenwick tree by y coordinate. Second index is the Fenwick tree by second coordinate. So each element will maintain the sum of all sums. I need two more indices, so I'll just use x and y from P of I to I and y from P of j to j. X, y. Oh, basically, this is a new marker just from the box. They just oh, this looks fine. So this element of array F will correspond to sum of all elements inside the segment. So this is I j. So this is P of I. This is P of j. So this element of array F will contain this sum of elements in array A. And now, how you implement this operation? What operations do we need in the Fenwick tree? Just raise this. So in Fenwick tree, we need to find the sum on some. So in regular Fenwick tree, we find the sum on the segment. Yep. Using two sums on the prefixes. So we have this prefix minus this prefix will equal to the sum of on this segment. So in two-dimensional case, we just do the same trick twice. So when we need to find the sum on some rectangle, we first split this rectangle into two like prefixes. So we have this element minus this element. And now we split both of these like prefix rectangles into like two corners. So we calculate sum on this rectangle like difference of this rectangle minus this. So we have, it's too complicated picture. So we take this rectangle plus minus this. This will give you the sum on this area. And then we need to subtract this area and add this area. And this will give you the sum on this rectangle. So when you want to calculate sum on this rectangle, you kind of want to split this rectangle into some sum on prefixes. It's like two-dimensional prefix sums, something like that. So you have two-dimensional prefix sum is just sum on all elements to the left and up. So you have this sum minus this sum minus this sum plus this sum. It will equal to the sum on this rectangle. And now you want to be able to calculate the sum on these rectangles like this. So given this point, you need to be able to calculate sum in this area of your two-dimensional array. How to do it using these pre-calculated sums? again, you do it the same way like in Fenwick trees, but do it twice. So you start from this point. This point contains the sum of some segment of some some rectangle. You add it to your result, and then move to this point. When you move to this point, you have some sound rectangle. You add it to your result, move to this point. You have another segment, move to this one. That's all. Now you move from this I coordinate to this. So you move from here to here and calculate this. Here you have some sum of this rectangle, plus this rectangle, plus this rectangle. Then you move here, take this rectangle, plus this rectangle, plus this rectangle, and so on. So the code again, I just write the code, yeah. So the code is simple. So if you start from point ij and you want to calculate this sum in this array, so you start from point ij. Let's say like here. Let's have x equal to I while x is at least 0. This is again, this is a one-dimensional case. One-dimensional case works like this. One-dimensional case works like this. We just add a result of x to your result, and x equal to x and x plus 1 minus 1. And if we want to do the same in two-dimensional case, we just make the same loop twice. So we start from x equal to I. I can do it in C++ type, make it a for loop, but I will not do x at least 0. And here we make another loop, like y equal to j, while y is at least 0, we add value xy, and then move y. Y and y minus 1 minus 1 plus 1. And after this while we move x. Like this. So again, that's all. You just have the same code, just apply it twice by first coordinate, by second coordinate, and in the end you will have the result in the beginning. Practical of some segment trees. Basically all the examples we discussed all, I believe, in the first lecture. Now, finally, I want to discuss the two-dimensional sparse tables also. Two-dimensional sparse tables. Again, let's talk. So how the regular sparse tables work. So in regular sparse tables, you have table Mij, and this contain minimum on segment from I to I plus 2 power j minus 1. Yeah. Again, we discussed it last lecture, yeah, right? So this is a regular sparse table. You have this array. This array contains minimums on different segments of your array, and you do some pre-calculation in log n time, and also query in constant time. So this is one-dimensional case. In two-dimensional case, again, we will do all the same thing, but twice. So we will have not two-dimensional array, but four-dimensional array. So we need four-dimensional array to maintain all the we need. So we'll have I need 4 letters. Okay, let's have I, J, K, and L. It will be minimum on a segment from I to I plus 2 power j minus 1 by y coordinate, by one coordinate, and k plus k to k plus 2 power l minus 1 by the second coordinate. So I need to maintain this 4-dimensional array to make my 2-dimensional sparse table. How fast can I calculate it? I can calculate this 2-dimensional array in the same way I calculate one-dimensional sparse table. I just do the same twice. Each time I split my segments into two segments by one coordinate, then I split into segments by second coordinate, and then recalculate these minimums. So I can calculate all these minimums in linear time by the size of this array. So this array has size n square log square. So here I have this log square in this precalculation time, like in all. This works in log square time also, obviously. So here I have this log square time complexity in precalculation, and also memory complexity will be increased in. So this amount of memory I need for this data structure is again it's n square log square, because I need all these different rectangles. And how to answer the query again? So to answer the query, you have this rectangle. You need to cover this rectangle with the rectangles from your array. So again, you find this segment by the first coordinate, cover the segments with 2 segments, and then you have your segment by the second coordinate. So you cover this segment with 2 segments here. And now you take these 2 segments. In each of these segments, take these 2 segments. So you have these 4 rectangles. So you have this first rectangle, this second rectangle, the third rectangle, the fourth rectangle, and these 4 rectangles covers all your rectangles. So you get minimum here, minimum here, minimum here, minimum here, and find the total minimum in your rectangle. Let's also solve query also rectangles that. Okay. That's basically all I want to discuss today. I have some more problems if you want to discuss them. Okay, we will discuss one more problem. Good. Good. Okay. Let's have one more problem just to show you another technique. Okay, it's not a technique, it's also kind of important, so we'll talk about this technique later in this course, but just let's start it now. Let's solve the following problem. It's called, I don't know, I don't remember the name of this problem. Let's go. No. So the problem will be the following. So we have some points. Too many. Let's have 8 points. 8 is enough. So let's have some points, and these points correspond to some objects, right? Let's make it more practical look like. So let's have just because every time somebody asks what is the practical use of your data structures, let's find some practical use for this expression. Let's have imagine you have some online store. So you sell something like, what can you sell? I don't know. Some computers. Yes. Oh, boring. Okay. So you have some computers, and this is too boring. What can you sell? trees. I need something complicated to have various types of. No, give me something not very boring, not very technical actually. Let's have something funny. Cubes, it's not funny. Rubik's Cube. Donuts makes sense. Makes sense. Yeah, this sold. Okay, you sell donuts, and you have various types of donuts. Good. And each donut is specified by 2 parameters. I need 2 parameters. Donut obviously have 2 parameters. Is size of donut, size of the whole donut, right? So each donut is obviously specified by 2 parameters. This outer radius, okay, and is inner radius. Yeah? It makes sense. No, it's hard to have. How to measure flavor as an integer? It's kind of complicated. So I need two numeric parameters. That's good enough. So you have various size of donuts, and so each donut is specified by 2. So let's call them X and Y for simplicity. So you sell some donuts. It has 2 parameters, and each donut is specified by these 2 parameters. And you kind of want to be able to select donuts in the given constraints. So you're given some constraints on these 2 parameters, and you want to find all the donuts which satisfies your constraints. So we have this Y, this X. So someone give you some constraints that X should be between X1 and X2, and Y should be between Y1 and Y2. Price is nice. Radius and yes, weight and price. Yeah, it makes sense. Okay. Actually, doesn't make sense. So we have some 2 numeric parameters. Okay, and you want this first parameter be inside this range, the second parameter be inside this range. That's all. That's the whole problem. Find all the objects which satisfies this constraint. Or find any object, or find number of objects, or find anything. So do something with this range of objects. So how it looks when you have 2 dimensions. So you can look at this as a 2-dimensional problem. So we have this 2-dimensional plane. So each object is some point on this 2-dimensional plane, and you want to find all the objects inside the rectangle. So you're given a rectangle. And you need to find all the points inside this rectangle. That's all. That's how this corresponds to reality, actually. That's actually kind of useful. Cool. So how to do this using segment trees? First of all, you can do it using persistent segment trees. I will leave you as an exercise because we're too late. But you can answer these queries using the persistent segment trees. You may think about it. We also talk about persistent trees today. I want to show you another technique. Actually, persistent trees are very powerful techniques for operations like this. Why am I using this? I don't need this part. Okay. I need only this part. Let's make a segment tree or x. So let's find the x coordinates of all points. And build a segment tree over these x coordinates. Like always. Now, inside each of these, so again, each node of this segment tree corresponds to some segment by this x coordinate. So inside each of these nodes, we will maintain all the points inside this x segment by x coordinate. So we'll put not one value in each node, but all the points which belongs to this segment. And we will maintain these points sorted by y coordinate. So let's just enumerate them by y coordinate for simplicity. So this will be 1, 2, 3, 4, 5, 6, 7. So I just enumerate them by y coordinate for simplicity. So in each node, we will maintain the list of all points inside this segment by x coordinate, sorted in by the y coordinate. So here we have lists of 5. So here we have simple lists: 3, 7, 2, 6, 8, and 4. In the second layer, we will have lists of 2 elements. So here we have lists of 1 and 5 sorted by x. So first we have 1, then we have 5. Here we have 3 and 7, here we have 2 and 6, here we have 4 and 8. Again, each of these lists is sorted by y coordinate. Here we have all elements from these 2 lists sorted by y coordinate. So we have 1, 3, 5, and 7. And here, that's fine. Okay, we have all odd numbers here, or even numbers here. Okay, here we have 2, 6, and 7, 8. And here we have all elements. That's all. So let's maintain this segment tree. So again, this is segment tree, but each node of this segment tree contains not one value, but a list of values. Yeah, this looks exactly like what happens when you make a merge sort. You can call it merge sort tree. It's not very common, but again, here exactly. If you look about how merge sort algorithm works, it works exactly like this. You start from the single elements. Each time you merge two arrays into one sorted array, and so on. So you can build this segment tree in n log n time. So in n log n time, you can build all these lists. You can just take 2 lists from your children and make a merge operation. So total time will be linear among all the size of this list. The total size of this tree is n log n. Okay. Now, how this tree helps you to answer your queries. So again, you have this query. Oh, query is a rectangle, right? So you take this rectangle and make a query. First, you make a query over first axis. So you take this x1 and x2, and you try to make a regular segment tree request on a segment on a tree. So again, you start recursion here. Go here, go here, go here, here. You need to take this segment. So this segment is inside. And then you go back, take this segment. So this segment is supposed to. And now you find all the points which are inside your segment by the first coordinate. And now you need to, inside each of these nodes, you need to find all the points which are inside your segment by the y coordinate. So here you again just have this. Let's have our marker. So this is first coordinate, this is second coordinate. You need to find all points between these 2 points by the y coordinate, but they are sorted by y coordinate. So we can use binary search to find these 2 borders in this sorted array. So first border will be here, second border will be here. So we need to output these 3 as a result. And now we go here and see that the first border will be here, second border will be here. So we need to output these 2 and 4. So again, we need to find all the points inside the rectangle. First, we find all the points inside the segment by x coordinate just by using standard regular segment tree request. So we start from the root and apply the same recursive procedure to find these two nodes. So these two nodes corresponds to this segment by x coordinate. And now inside each of these two nodes, we need to find all points inside this segment by y coordinate. But they are sorted by y coordinate, so we make two binary searches to find these 2 points, and all elements between these 2 points actually corresponds to some points inside your rectangle. That's all. So if you apply it like this, you will have log n time to find these segments. In each of these segments, you need to find you need to apply binary search to find these 2 borders, and it will cost you log n time to find the segments and then log n time to find those. So total time will be log square. Cool. It can be improved to work in log n time using a technique called fractional cascading. I will not discuss it today, but you can find it. It's actually not. I will discuss it. Let's go. It's not very late, right? Let's discuss it. You can do it without this additional logarithm using a technique called fractional cascading. Let's discuss it. Actually, in this case, it's not even fractional. It's just cascading. It's not. We don't need. What is the idea? So let's see. We need to find the. Let's have these 2 positions. So we have these 2 positions, y1 and y2, and we need to find these 2 positions in these 2 sorted arrays. Instead of making these 2 binary searches, we will make only 1 binary search, and we will make binary search in this first array. So we'll take this first array in the root, and in this array we will make a binary search. So for example, we need to find y1, so y1, let's say y2. Y2 is between 5 and 6, so y2 is somewhere here. So we will make 1 binary search and find the position of y2 in this big sorted array. And now when we move to the children, we can actually recalculate this position in constant time. How can we do it? Well, let's see. If we move to the left, then some of elements of this array actually move to the left. So this array is split into 2 parts. Some elements move to the left, some elements move to the right. Let's look on all elements move to the left. So in the left, we have this 1, 3, 5, and 7. So if we know that our current position is between 5 and 6, we know that if we move to the left subtree, we will be between 5 and 7, always. So our position depends only on our position in this array. So if we know position of y2 in this array, we know the position of y2 in this array. We don't need to make a binary search to find it. So we always, when we stand here and move to the left subtree, we will be here. So we don't need binary search to recalculate the position. We may pre-calculate for each position in this array the position we will be when we move to the left subtree. So for each position in this array, we will pre-calculate the position we will be if we move to the left subtree or if we move to the right subtree. If we move to the right subtree, we will be between 4 and 6. We will also pre-calculate this position. This just can be done in linear time. In linear time, we can pre-calculate for any position the corresponding position in the children node. So for this position, we will pre-calculate where we'll be when we move to the left subtree, when we'll be move to the right subtree. So if we move to the right subtree, we'll be between 4 and 6. So we will be here and this array. So we will do it before the query. So just when we calculate all these 3, we will pre-calculate all these moves. So for any position, pre-calculate these two positions. And now we don't need to do binary search. We do binary search here only once in log n time. And when you go here, you just use this pre-calculate position and move here. And here, when you move to this child, you look on the elements. So 3 and 7 are from this child. So when you move here, you always be between 3 and 7. So you know that if you are here and move to this child, you will end up in this position. That's all. That's the whole technique. Very simple, actually. So yeah, what is the technique? It's kind of the idea is very simple. You have multiple binary searches. Instead of making multiple binary searches, you make only one binary search in the first array, and then use the result of this binary search to make all next binary searches in constant time. Because you actually don't need these binary searches. You already know your position. You know your position in this array. It means you have enough information to calculate your position in this array. So you move here, then you move here, you move here, and each time you move from one element to its child, you know your current position in this sorted array. That's all. So if you just pre-calculate all these moves, then you will have log n operations and only one binary search here. So it will be log n for this binary search plus log n for all these moves. So total time will be log. Whew. Is it possible to change the elements? It's complicated. Simple answer is you can change the elements, but it's complicated. We will talk about it in the future lectures, I think. So again, this structure is kind of fixed. So if you have some number of points, you build this data structure. And if you want to add another point to your data structure, it's kind of painful. Yeah. So if you try to add another point, then you need to recalculate the whole data structure because these orders will be changed. So you need to add this point in all these segments and so on. It's complicated. It's actually possible to do it, but it's complicated. If we have, I hope we will have enough time to discuss. So if you want to just put this point inside this sorted arrays, you can do it using binary search trees. So when you want to maintain inside each of these nodes, so instead of having the sorted array, you'll have to need binary search tree inside of this node. But to maintain this outer segment tree, you kind of need to some special binary search tree because we'll talk about it. If you just want to change y coordinate, it's you need to maintain these arrays not as sorted arrays but as binary search trees. So when you change the y coordinates, you iterate on all these nodes and kind of remove this element from the binary search tree, change one coordinate, put them back. So binary search tree will allow you to do these operations in log n time. Yeah. I believe that's all. That's all for today. So again, thank you for joining me today.